talk or maybe discuss about advances in quantum technology based on the ion trap platform, which is precise and versatile platform compared to other candidates. I will take you through how to develop a quantum computer, highlighting the technologies involved in building the quantum computer. I will also show that this platform is suitable not only for computing but also for sensing and also for simulating many body physics, making this platform superior compared to other platforms. In the context of like other platforms are mostly purpose specific. So here, like you can see, like this image, like where like you can see how many ions. 7 ions are moving, and they are moving together. So here, each blob of light represents a single atom, and these are actually barium ions held in inside ultra high vacuum system. And in order to like keep it inside a vacuum, you need a potential because this is charged particle. And if you see, there are 6 ions, right? And the inter-ion separation is in micron order, but still it is possible to individually address, individually control. So that it is at that level, like controllability makes it essential for computing purpose. But it is not only suitable for computing, but also suitable for other things like it can be treated as a sensor, it can be used as a simulator. Okay, so here you can see the image. So this is the first classical computer. The size of it is, you can see from here, like it is almost, it's covering a room about 1000 square feet. This is and the basic building block for this classical computer was like vacuum tube. It is before our independence. So that time this was the size of first classical computer, and the basic building block or classical beat, what you know, that was a vacuum tube. And the vacuum tube was basically like it has a cathode and anode, and in between the cathode and anode there was mesh which was controlling the flow of current. By that way, you can you can have a threshold. Above threshold it will be state 1, below threshold it will be 0. Now if I go to the second one, so here now how the classical bit has evolved. Like initially it was vacuum tubes. Then during 1947, so we got the first transistors. You see the size of these transistors. So yeah, then the size of this transistor, it is reduced over the years. And this is the pictures, like you can see how the size is changing and how size is now. Like this, the final picture you can see, like in 1997, you can hold in your finger the chip size, you can see. So the transistor, you know, this is known as classical bit, where you have only 2 states. This is also another important slide, because you see how the size, the left one, if you see the left figure, how the size of the classical computer is changing over the years. The reduction in the physical size of the processor also. And on the right side, if you see, the right side, it shows how the number of classical bits meaning transistors inside a processor, has increased over time. So now from 2010 onwards, it is kind of saturating. It is not like number of total transistors inside a processor. It is not improving that much, because if you see this one, the size of transistor, now the size of transistor is close to the size of an atom. So if it reaches to that level, then already quantumness is introduced. So it may not, so the first criteria is that if the size is so small, close to the single atom size, it may not show the classical behavior. It may show the quantum kind of behavior. So then why not quantum computer? So this is the first step. And the other thing is that there are certain problems like traveling salesman problem, so-called known problems, traveling salesman problem, or prime number factorization problem, or search for unsorted database. These problems you cannot solve by using classical computer, or even if it is possible, it will take huge amount of time. So it is not the speed wise, it is not fast, and also it is not energy efficient at all. So in one way, the size of transistor has reached the scale of an atom. So that is why the purpose is to develop a quantum computer. Why then classical computer? So the limitation is that beyond this size, this is not feasible. Even if technologically possible, you can reduce, but it will not behave as a classical bit. So that is what I want to say. And secondly, these are the problems which is not possible by, or maybe it will not cost effective or energy efficient. That is why you should go for quantum computer. Now, other than this this so-called problem, there are many body physics, which is not possible at all in classical computer, because it's a many body physics. Like the well-known problem is phenomena like high temperature superconductivity, or other phenomena like this. You see this quark gluon plasma, which is basically, you need many body. You have to handle with many body system, right? So then you have to deal with natural phenomena. So in that sense, if you develop quantum computer, it will be much easier, because you are handling, because nature itself is a quantum, right? So you are handling and you are using quantum bit to simulate all these natural phenomena. So that will be much easier. So that is another purpose to move forward in developing quantum computer. Now, the third problem is that quantum network. You all know we are moving towards cryptography, right? Like now, classical network or the things, it is possible to hack. But if you have your network made up fully based on quantum physics, it is not possible, as you know, because of superposition principle, right? So that is also another thing of developing or moving our technology towards quantum. But is it true now that quantum computer will be replacing classical computer? It is not true. Quantum computer will be a different kind of computer, not just bigger or better version of the current classical computers. So there will be, like, for small problem, like for some multiplication problem, if I want to use quantum computer, that will be cost again. So it will be problem oriented. For what purpose you want to use quantum computer and what purpose you have to use classical computer, that have to be differentiated. So it is not going to, if we have quantum computer in future, it will not replace the classical computer, but it will be definitely bigger or better version, and it will be used for those kind of problem where it will be faster and it will be cost effective and time consuming. Now, in order to realize quantum computer, you need some rules and regulation from where you can start. Like, you need a basic building block. Like for classical computer, you have a classical bit like transistors. In case of quantum computer, is a quantum bit or qubit. Now, any qubit cannot be, you cannot use to develop a quantum computer. It has to satisfy all these statements, which was given by Davincenzo. The first one is that the qubits has to be well defined. So it's and it has to be scalable. Like, we are not going to deal with only single qubit. Yeah, qubit is powerful, but it is not like only one qubit is sufficient to solve all other problems. So it has to be scalable. The second one is the initialization of the qubits, initialization or the preparation of the qubits at your will. Like if we need to prepare in some states, we can prepare with 100% fidelity or at least very high fidelity. Third one is the long relevant decoherence time. So the structure or construction wise, classical computer and quantum computer, they are two really different things. All of you know. So the system here, it is inside vacuum, right? Vacuum. Why we put it inside the vacuum? Because we want to avoid the interaction with the environment. So that is why if there is interaction, then it will not be coherence. So then all the signal to noise ratio will be very bad, and then the output will be very bad also. So you cannot rely on them quantum computer. And the fourth one is universal set of quantum gates. This is like for classical computer also, we have a universal set of gates, digital gates, NAND gate, which is a universal gate. So here also we will have a similar kind of, we need a similar kind of gate. If we want to perform some, if we want to executable, hello, can you hear me? I am audible, right?
Yes, yes, we
Yes, sir,
can
you
hear
are
you.
audible.
Okay. So I just got a message like a network connection problem. Okay, thank you. So so that is why we need not only gates but universal set of gates so that we can perform any kind of algorithms. We can implement any kind of algorithms. We can also design different kind of quantum circuits. And now the third thing is that qubit specific measurement capability. Measurement is really a problematic in quantum computer, because if you measure, then the state will not be there anymore. And since the way we measured, it's based on mostly spontaneous emission, right? And it is isotropic. But we cannot. So we're going to measure the photon, right? Number of photon count. So we have to have the detector at one place. We cannot move so it is very challenging. So that is why your measurement system, you have to develop your measurement system such that your signal to noise ratio will be enough so that you can differentiate between higher state and lower state. So these are the 5 basic criteria or requirement to build a quantum computer. Now there are many candidates, as I was telling you in the beginning. Of course, Trapdown is there, and I actually claim it is superior compared to other platforms. And the other platforms is like superconducting circuits, Trapdown and atoms. They are same because those are natural qubit. But the other like superconducting circuits, these are synthetic qubit. So that is also another advantage of trapped ion. So like if you want to have more than one qubit, then you can have more than one similar kind of exactly similar qubit. But in case of superconducting circuit, it is man-made. We are developing this qubit. We are building we are constructing this qubit. So even if we have many qubits, they may not behave similarly in the same way, or in a proper way of saying it, like the fidelity will be different if we measure the fidelity. So it is very difficult to have exactly similar kind of qubit in superconducting circuit. But in case of atom or atomic ion, whatever be the number of qubits you need, you can generate and they will be similar because it is a natural qubit. So if you see this comparison with other qubits, you can see in case of, so here also you can see the important thing what I want to point it out, like the power in order to execute some problems, it's around 2 kilowatt. In other cases it is higher. For all other candidates it is quite higher compared to the trapped ion systems. But one disadvantage you can see over here, that the number of qubits till now is used 24, but this is not, this is a bit old slide. So now it is around 50 or 60. It is done by some company, I think it is Quantinuum. They are using 50 to 60 qubits. But compared to other like superconducting qubits, they can have many more qubits. But the fidelity will not be like the one we can have in case of atom or ion. But the problem is the controllability in case of trapped ion systems. We will discuss all these things later. Now, this is also the other slide, which is also showing the comparison between all other candidates. And you can see like the fidelity wise and the coherence wise, it is far, far away from the rest of the candidates. And coherence is, I mean, all of you know, like if you have coherence, then you can perform any, like you can use it as a quantum computer can use it as a simulator, or you can simulate, you can use it as a sensor. But if decoherence comes, everything will be gone. You cannot use it at all. So in that case, in that respect, the coherence time wise, you can see this qubit like it's a more than millisecond. It is recent papers like a few years back, one group from China, they have shown that they can store the I mean, they can perform the qubit, perform the quantum algorithms, and the coherence they can maintain up to 1 hour, which is really high. But even with not like 20 ions, 30 ions, the number of ions was very less, 5 or 6. Okay, now since I'm talking about classical beat and then I'm moving to quantum beat, just to give you a little bit of idea, all of you know what is classical beat, right? And we are telling that transistor is used as a classical beat. So we can think it as switch, light switch. When it is switch is on, the light is on. When it is off, the switch is off, the light is off. So classical bit is something like it has two states, either on and off. But quantum bit, it has two states, on and off, but it has also intermediate all the states. So you can compare with a slider or dimmer. So like including on and off state, it has many intermediate states. So that is the difference. So like quantum bit, usually we represent it as a Bloch sphere. So you can see that 0 and 1, like the two poles are the two states, and all the states on the surface of the sphere are also quantum states. So that is the difference coming from quantum physics. Like you have off state, you have on state. In case of like you say, the state is denoted by 0 kT and 1 kT, and also the psi, which is the superposition state. So the state like ion can be or atom can be in simultaneously both 0 and in 1 state. And one more important thing, because of this like exponential growth of Hilbert space in case of quantum bit, like I have given you an example. If you have 55 qubits, then you need 1 TB of classical memory to store. So this is huge. For classical computer, it is not like that. Classical computer at a time, your qubit either will be in 1 or will be in 0 state. But in case of quantum bit, it can simultaneously, it can be 2 to the power n states because of the superposition principle. So yeah, this is what I talked about it. Now you see the chain of ions. There are at least 10, 12 ions, and all like each block is a qubit. And yeah, and more the number of ion, the more the qubit you will have, you can develop your system. So yeah, this is I have already told, like quantum computer is not going to replace classical computer, but it will be problem specific. What kind of problem you are going to deal with? If you want to solve many body physics, then quantum computer is better, but it is not going to replace classical computer. The other thing which is very important, like like the technology, from the technology point of view, it is very challenging to develop each and everything because it is a quantum. And the system is inside a vacuum. You have to keep it inside a vacuum. So like we are in a niche era. So, I mean, the system is very noisy, like our qubit is very noisy. Single qubit fidelity is okay, but when you go to multiple qubit and you want to control individual qubit, then the signal will be very noisy. That is why it is named as a NISQ, noisy intermediate scale quantum computing era. So here, what we have to decide whether we have to increase the number of qubit. If you see the right side figure, bottom one, the y-axis is a circuit width, meaning that whether you need to increase the number of qubit, or if you see the x-axis, which I'm saying the depth, or whether we need to increase the depth of the circuit. That is very important. The ideal thing would be like if we go diagonal, that we can simultaneously increase number of qubits, and also you can have we can increase the depth of the circuit. But that is not possible. That is quite challenging because our system is very noisy in this era. So we have to choose any one. So I will show also which one I'm choosing in order to solve some problems that I will discuss later. Okay, so now I have already discussed with diving into criteria, like those criteria has to be fulfilled if you want to realize quantum computer. So this one we can think of it as a temple, our quantum computer. Now temple without a pillar, it is not possible. Pillar has to be very strong enough so that it can hold the whole temple, right? So here also, in order to, I have divided into 4 pillars, which are like very basic and which we need, we have to develop very well. The first one is trapping of ion. As you can see from the left side figure, first one is trapping of ion. The second one is the controllability, meaning how good you can prepare your system, how you can control like whatever you want to prepare, that you can do it very well with high fidelity. And the third one is the readout, which is also very challenging. That depends on the photon counter or the quantum efficiency of the detector, which counts the photon. And the fourth one is the gates, like the gate, quantum logic gates or the universal gates, what you are preparing, how good they are, how good to implement, and what is the fidelity of am I getting some questions? I don't know, it is popping up some questions, so but I cannot see those questions. Shall I continue or I will reply if? Oh, okay. The superposition, like, in classical computer or like the classical bit, it can be either 0 state or 1 state. But in case of quantum, it is probabilistic, right? So there will be like both states is possible. Either you can have your atom in 0 state or in 1 state, but the third state is the superposition state. The atom can be 50% time will be in the 0 state, and also 50% time will be in the 1 state. That state also you can prepare in case of, because that is based on quantum physics. So that is why. Oh yes, simultaneously. That is the difference between classical bit and quantum bit. Like in case of like, I mean, that will be clear in few slides. I'm going to explain how you can prepare that kind of superposition state. Then it will be clear, I think. Okay, so now let's, yeah, I'll discuss that thing. Okay, how we can prepare the superposition state and how it can simultaneously be there. I will discuss. Okay, so now let's start with the first pillar, which is, okay, before going to the discuss about ion trapping. So the ion what I work with is a barium ion, and you can see the energy level diagram over here. So these H to P transitions, these are energy levels, right? And so H to P is a dipole transitions. So we are using, so in order to address these transitions, we used 493 laser. And from D3/2 to P half, it's also dipole, we use 650 lasers. So now there are other lasers, like from, you can see S half, from minus half to D5/2 minus half. That laser is 1762 nanometer laser, IR laser, and that laser is used as a qubit laser, and this is quadruple transitions. So here you can see the the pictures of many more ions. Each ion is representing a qubit. Like here I have shown you. You have taken one ion, and so this ion is equivalent to a two-level state. And the way to represent, or the way to understand, you can understand in way like in terms of block spheres. Like here I told, like 1762 nanometer is a qubit laser which is addressing S half minus half MJ value Gman levels minus half to D5/2 minus half. So on the block sphere, if you see, it is S half minus half is 0 state, and D5/2 minus half is 1 state. Now let's go to discuss about the first pillar of our temple, which is trapping ion, how we can trap ion, because each ion will be one qubit and we want to deal with many more qubits. How to do that? So since ion is a charged particle, atomic ion is a charged particle, right? So how to confine a charged particle in space? So the first thing comes into mind is the static potential. If you can create a static potential or DC potential, then you can confine. But in space, meaning from three directions, it is not possible by having only static potential, because that will not satisfy Gauss's law. Or Ehrenfest's theorem is also there. So then the right side, if you see the picture of the scientist Wolfgang Paul, he came up with an idea. In order to trap charged particle in space, you need both RF and static potential, meaning you need both alternating potential and DC potential. So if you see this animation over here, so here the green colored arrow which is oscillating, and if you look carefully, you can see the arrow, the position of the arrow is changing. So we are applying alternating field to those electrodes, and along the z axis, which is the color of that one is yellow, along that axis we are applying DC voltage. So along the z-axis we are applying DC. By that way we are confining along that direction, which we usually call axial direction, and the other two direction is radial, where we are applying alternating field. Now the right one, where I have written linear Paul trap. So this is the electrode. So all the things over here are made of metal, stainless steel, and all these, as it is clear from the figure, you can see all these are electrodes, and I put the name here RF blade, meaning I'm applying RF voltage or alternating voltage, and these are the DC rod where I am applying the static potential for the confinement along the axial direction, and on the RF voltage I'm applying RF potential to confine along the X and Y or in the radial direction. Now, how it is confining the atom or atomic ion? If you see the other animation, which is on the left side, I hope you can see, the ion is trying to get away. But the time, if you take a snapshot of this potential from the point of ion's perspective, so the time ion starts leaving the potential, by that time, because it is alternating or oscillating voltage, right? So it oscillates. So when the ion sees the potential is lower, it starts to get away from the trap. But since it is oscillating, the potential itself is oscillating. It is switching back and forth. So ion is unable to get away from the trap. So this is how, that is how we are trapping like ion. in radial direction, and the other direction, like along the axial or along the z axis, we are applying DC voltage. Now, how it is trapping in the radial direction? If I show you this mechanical analog, you see this shuttle potential. This is the rotor, like this is a ping pong ball, and the potential, you see the right hand side, the shuttle potential plane, and I want to keep the ping pong ball, the yellow colored ball, in the left side. You can see. So it depends on how fast you are rotating this saddle potential. It has to be faster compared to the motion of the ping pong ball, right? If the motion of the ping pong ball is higher compared to the rotational frequency of this saddle potential, then you cannot trap. Similarly, in case of iron, along the radial direction, you can think it as of like so you can get an analogy how we can trap the ion. And this is the effective potential, which is the total potential, like both RF and DC. Here, one thing is important over here. There is no sound at all in the animation. This is just animation. There is no sound in the animation. Okay, so here I have shown you the schematic of the electrode or the linear Paul trap setup over here. The important thing here is the trap volume. Like if you see the side view, the distance between the tip of the RF blade from one blade to another blade and the distance between two DC rod, that will be the trap volume. So there, so that position, you can, the ion will be there. That is the minimum for the ions. So that is very important. So this electrode separation is very important, because that will tell you how many ions you can trap or how many qubits you can have in your setup. So the setup what I developed or I worked with, that is kind of big. So I can have almost 30 ions. Okay, this is the first thing I did, like trapping dust particle. You can see the video over here. This actually I developed during my PhD. So just to show like how it is easy to trap charge particle. You can see the electrode. So similar, you can actually get an analogy. So the ring, that is where we are applying RF, and the other two end cap or DC, where we are applying DC. So inside this rod, I mean inside this ring, you can see a blob, right, which is very bright. So we shine the laser, and then that is why you can see the blob. That is dust particle actually. So that is how that is the first step to realize how we can trap charge particle. So this was my first step to realize, I mean, trapping an ion. Though dust particle is not charged, but you can introduce charge in the dust particle. Hope you all know. So now let's get into the process how I had developed the setup for in order to realize quantum computer. So this is the real trap setup over here in the left side. Hope you have seen my arrow over here. So before I have shown you the schematic, so, and this is the real life. So this is the real trap, and when it is mounted on the vacuum plunge, so you see there are a lot of wires, cables, it is connected. And on top of this flange, the trap is mounted. Besides the trap, there is also another extra position. Like you can see this another mount is over there. If you see the schematic over here, it is written this is collecting lens. Okay, so this lens we usually put it inside the vacuum in order to get more number of photon count. So that is why the stage or another mount is there for the lens. Now, once you mount it inside the vacuum plant, then we put it inside this vacuum chamber. You can see the vacuum chamber over here in the schematic, and this is the vacuum chamber, and all these are like on the flange. You can see something is poking out. That is the fit through, where we used to give potentials to create confinement for the ion. And this has to be the vacuum has to be very good. So that is why we have different kind of pumps which will bring us to the pressure actually 10 to the minus 11 millibar. And this is the like real setup. Like the vacuum chambers are over there, and these are the coils. So you can see these are the coils, the copper wire you can see. These are the coils. So coils are used. So these coils are known as Helmholtz coil. So that is producing a magnetic field, and all the optics you can see just to steer all the lasers so that it can talk to the ion. Because once you trap ion, you need to cool it down, and then you need different lasers to prepare different kind of states, to say different kind of phenomena, to different implement different kind of circuits. So that is why all the optics are outside, and it is so the vacuum chamber has different windows, many windows. So for this one, it has 8 windows. Out of 8 windows, we have able to access at least 4 windows for the optical access. Now, once and you have everything ready, then you can try to load the load ion. So you can see the images here at the bottom. I showed you the cloud, ionic crystal, single ion, and you can make also this kind of rotor, which is just at the bottom of the ionic crystal image, the rotor. So by playing the amplitude of RF and DC, you can prepare cloud, you can prepare ionic crystal, you can give different kind of set. So that is how amazing it is. And you can even trap single ion, not only cloud, you can trap in single ion. The experiment what I'm going to show here, I'm going to present here, that is based on single ion. Now let's get little bit details about how I'm getting these ions. So here, the electrodes, I put it in the little bit simpler form. And this is the image you can see. This is from inside the vacuum chamber. So the trap is over there. The electrodes here you can see, and the this side, okay, there is this side. This is the atomic oven, and you can see also all the lines. These red lines. These are basically lasers. So what is happening? So this atomic oven is basically is a tube which is made of stainless steel tube or tantalum tube, and we put inside barium metal. So barium, you cannot get it in a powder form. You have to make it a powder. It is a solid. And one important thing is that barium actually it reacts in air. So you have to prepare all the oven inside a vacuum. Otherwise, if you prepare it outside, what you have to prepare? You have to put all the barium inside the tube, and then inside this kind of tubes, what I'm showing it over here, you see those tubes, and those tubes have like source and ground, so that current can be flow from one side, and the oven needs to be heated up. So that heating will be resistive kind of heating, and those ovens actually fixed inside the vacuum chamber. You can see it over here. So what is happening? You prepare the oven. Now you cannot you cannot fill the oven with barium, keeping it outside, because barium reacts in air. Then it will prepare barium oxide. So then it will be very difficult to get barium inside barium ion inside the vacuum. So that is why you need to prepare inside the vacuum chamber. Then you fix the oven. That is the way I'm saying it is easy, but that it is not that easy. It is very challenging. But nowadays it is a bit straightforward. So you can now fix the oven over here. Now you and the oven is connected to your power supply. So the current is flowing, and this kind of oven, what we develop, it is such that the material will be it will be heated up, resistively heated up. So the heat will transfer from metal body to the barium, what is inside the tube. Then barium vapor will come out. And so barium vapor, you see the tip of the oven over here. So the barium vapor will come out like this. It has to come close to the trap center. Like over here, you see, this is the trap center. You see, like this is the atomic beam. Here in the schematic, have a look over here. And so it has to come through the trap center because all the lasers are aligned to the center. If it is off-centered, atomic beam is off-centered, then you will not have ion. So that is also another thing. The alignment of the oven and alignment of the laser has to be very well centered to the trap minimum where you're supposed to load ion. So now atomic vapor is coming, but this is vapor. Vapor meaning it is neutral. So, but I am talking about charge, right? So how we are going to do it? We are applying the laser, which is known as photoionization laser. So it is barium, right? So we have to take out one electron from the outer, like from the outer orbit. So that is why we are applying here laser. So this is actually people usually initially does this thing by using an filament. Filament actually, if you heat up the filament, filament will give off electrons, and those electrons will bombard onto the atomic vapor, and then it will ionize. But that was if there is so from the filament, when you heat it up, not only electron will come out, some other bad stuff will also come out that will deteriorate your vacuum quality. And there are also other problems because electron, so you are heating it up, meaning you are giving some voltage. You don't want to have any other stray voltage inside your trap because you are trapping charged particles, so that it is already having a potential well. Now, if you introduce another potential, that can disturb. So that is what you want to avoid. So that is why this is kind of technologically, I mean, it is developed over the years. Like people have found which lasers is good so that we can ionize the vapor. So yeah, so if ionize, now if you cannot, like if you have developed a potential, so it has a potential well, it has a depth, right? If your ions energy is quite higher compared to the depth of the potential what you have created, then you cannot load. Even if you have ionization laser, even if you have a cooling laser, you cannot, sorry, you don't have, I didn't talk about cooling laser. So that is why you need cooling laser. So you need to reduce the energy of ion which is being produced by applying photoionization laser. So that is why simultaneously you have to have atomic vapor, you have to have photoionization laser and cooling laser, particularly at the trap center where you're supposed to have or you have created the potential minimum for the ion. So this is challenging, and yeah, so this is the way we usually have the ion. Now, there yeah, on the right hand side, I just want to show you some kind of animation, but I don't, yeah. So you see now, so as I was telling, like S half to P half is dipole transition. So we are using this laser for laser cooling. But if you drive only these transitions, then sometimes the population or the ion will go to the other state. The state over here is this state, it's a metastable state. So ion can get stuck over there. But in order to cool it down, it has to be in this H2P cycle. Otherwise, you cannot cool it. So that is why you need this another layer continuously so that it can pump out from this state to P state. It will bring, then it will spontaneously emit to F state, and that is how you can maintain to keep the ion in this cycle. So this 650 nanometer laser, we usually call it as a repumper laser. It is repumping or deselfing laser, selfing the population from D state to P state. So for laser cooling, basically S, P, and D, these three states are involved, and the laser wise 493 and 650 nanometer lasers are involved. Now, here I'm just showing like here I'm how many lasers initially we have and how they are aligned to the center of the trap. So all the lasers you see, so they are mixed by using different optics, optomechanics, and then that is steering to the ions by using a particularly collimated, we say usually collimated lens, so that the focus will be at the trap center where the ions are trapped. Now, the lasers, so here, like if you see the energy level diagram of barium, you see I'm talking about a particular wavelength or particular, maybe particular frequency, right? You cannot apply any frequency and it will like transfer population from S to P. So you need a particular frequency. But all the lasers, ideally it is monochromatic, but in real life it is not monochromatic. It has a bandwidth. But to drive those transitions efficiently, you need to lock the laser so that there won't be any drift and you can reduce the bandwidth of the laser. So though lasers are ECDL, it is not free running lasers, but we have atomic cell where you can see atomic lines, and you can, if you have atomic lines close to that wavelength what you require for driving the laser cooling, then you can log that laser to the atomic lines. For 493, 455, those lasers are locked to the tellurium cell. For 655, that is locked to the iodine cell. Now for 493 and 650, we have also cavity, we have developed cavity in order to reduce the line width. That the drift of the laser frequency can be reduced by locking to the atomic lines, which are coming from the cells, gas cells. But if you want to reduce the bandwidth, then you have to lock it with the cavity. And then all the lights are going to the trap, and then the photons, you see, this is the collecting lens which is inside the vacuum chamber, which is collecting the photons, and here CCD, which is where you can see the image of each ion, the ions what I have shown in the previous slide, that is from the CCD image. And if you want to count the photon, then PMT is photomultiplier tube is there, which is counting the photon. And then you need classical computer again to analyze, because we don't have quantum computer. So quantum computer will not survive except classical computer. So that is why now the term which is popular is a hybrid system. We need both classical and computer. And I will also discuss in one of my experiments. So, and then the data is being processed through classical computer. One important thing over here to mention, the collecting lens, you see it is inside the vacuum chamber as it is here in the schematic. And it is sitting on the nano positioner. Nano positioner is like you can change the position of the mirror. Okay, so and that is being controlled from outside. So outside the vacuum chamber. So we don't need to give. I mean, we have a control from outside so that we can change the position. We can make it focus. We can make it off focus. Okay. So now, okay, now the first we learned about the first pillar. Now the second one is the state preparation. Whatever, if you want to do some kind of experiment, you have to prepare your system. You need to know the initial state. Otherwise, if you do some experiment, you cannot compare what you are getting as the output. So you need to know the input. Now, how well, how good you can prepare, that matters actually. So I'm showing some animation over here. You can see, like if I want to, as I was saying, the qubit meaning here two levels, but the levels what I have chosen is S half mj minus half to d5 by 2 minus half. So that is the two levels what I am using as a qubit. So I want to prepare in S mj minus half state. That is why I am using optical pumping over here. So both 493 laser and 650 lasers are on, as you can see it over here. Both 493 and 650 lasers are on. But here I mentioned 493 lasers supposed to have sigma minus polarization, so that the population will end up in mj equals to minus half state. And why I'm not talking about any polarization about the red laser, because I don't need red laser is very broad and I am using it as a recomper so that population will not get stuck in this state. So that is how you can prepare. But again, what matters is fidelity, like whether you are, so if you measure the population in S half minus half state, whether it is 100% or it is less, so that matters. So that depends on, so ideally it's supposed to be, but it is not in experimentally. So in our case, it was around 98%. So one of the main important reason is the beam what you are preparing, this sigma minus, whether it is perfectly sigma minus or not. That is much more important. So this is the technique which is known as optical pumping. The other technique is you can use this path, like from S half to D5 by 2. D5 by 2 is another metastable state. And then you use another repumper which is orange in color. The wavelength is around 614 nanometer. It can bring to P3 substrate. Then P3 substrate, it will spontaneously emit to S substrate. So this is another path. Why? Since before I talked about the optical pumping between S half, P half, and D3 by 2, then why I'm telling about this another path? Because if we use this, we have to verify where, in which case we are getting the good fidelity. I mean, the fidelity wise, we can prepare very well. So that you have to check, like which beam you prepare very well, like from the polarization point of view. Now we come to the fourth pillar, which is qubit readout. So whatever, like you prepare your state, then you did some experiment, develop quantum circuit, and you implement the quantum circuit. But now the final state to measure. So what you can measure, you have to measure in the form of photon count. So in this case, either you can measure, if you remember the block sphere, either you can measure 0 state or 1 state. You cannot measure superposition state. Okay, so that is the important thing. So here, how are you going to measure? Because we have to measure photon, we have a detector which will count the number of photons. So here again, we have to drive S half to P half transitions. If the population is in S half, meaning 0 state, then we will see the fluorescence. If it is not there, then it will be in D5 by 2 states. Then we will not see any fluorescence. So here you see, I'm again showing, like when I am signing for detecting the photons, I'm signing again S up to P half, but then there is always a probability to going to D3 by 2 state. So that laser is always on. So now if the population is in S half state, we will see this number of photon. You can see in the right side. But then what happens? Okay, this figure is becoming black. I don't know, but you can see this one. The right side on top, you see. So the signal is over here. Okay, whatever signal we got it here. But what is then in the right side? Then in the left side, this black histogram. So this is called histogram, right? So what is then this black one on the left side of this figure? So that is called as a dark count. When that is kind of property of a detector. When you do not have light is not falling on the detector, but still detector is showing some kind of signal, some electrical signal. So that is known as a dark count. And on top of that, if this is changing, that meaning this, if it is a property of detector only, that is giving completely the count coming from detector, then this will not change. This will be fixed, so that you can get a threshold, because that is important. You have to tell whether you have a count or not, whether it is a 1 state or 0 state. So that this is very important. So detection of threshold is very important over here. So that will tell you whether you will be able to detect 100% or it is less. So in order to do that, most of the time what we used to do, we increase the detection time, but that is also limited because of coherence. But if you see this dark count, what I was talking about, if it is changing, then it is very bad. That means your system, somehow the light is leaking from somewhere, from outside, it is going to the vacuum chamber, and that is being detected by detector. So the stray light has to be very well cut off so that it will not, detector will not see. So that is also another important thing. So in our case, we get around 98.4% state detection fidelity. And that is mostly depend on if you properly choose the threshold. Okay. So now I come to the third one. Fourth one I have already discussed how to detect. Now third one, the gates, the logic gates. So here, the left side, you can see the qubit, which is addressing two levels, 0 and 1. So in our case, it is 1762 nanometer laser. I have shown you before. Now, uh, you have already know the Rabi model, right? So atom is usually, in order to understand atomic structure, we start with a two-level system, right? So here we are driving the laser so that we can transfer population from 0 state to 1 state. Okay. So d5 by 2 state is a metastable state, it's not excited state. So if you populate d5 by 2 state, population will be there because it has a lifetime about 30 seconds. So this is what we have chosen for our qubit because of this metastable state. If it is a metastable state, it will be less noisy. If it is a dipole, then it will be much more prone to noise. So then what we see it over here, we prepare the system. Now we know how to prepare. If you see the pulse sequence over here, now we are playing with ion. You can think like we are playing with a single ion now. And we prepare the system in S half minus half state. Then we apply this 1762 nanometer laser for a certain period of time. It's tau over here, and I've written over here is a quadruple drive, meaning this is a quadruple transition from S to D. So I'm driving quadruple transitions. So this is on, then I'm measuring, I'm counting the photon. So what I'm going to see over here, so I'm going to see something like this. So at some point of time, if I'm changing this time, the tau, how long the laser is on, if I change the time, I can see some point of time, or photon, I'm not getting any photon, it is at 0 level, sometimes it is at 1 level. And it is basically the oscillation. So population is being it is being going back and forth between 0 state and 1 state, between A state and D state. And this top is known as, all of you know, is the Rabi oscillation. This is very important because this will characterize your system. So how fast you are going to prepare your gate, whether it is a X gate or any other gates or Hadamard gate, anything. It depends on how fast your Rabi oscillation. One more thing, already you know, I'm talking about the pi pulse or pi by 2 pulse we used to say. So what is pi pulse over here? So pi pulse meaning the population is going from 0 to 1. The time it takes, so here it is, I'm showing around 60 or 75, 75 around, let's say. So this is your pi pulse, meaning you prepare your system in 0, 0 state, then you apply pi pulse. After 75 microsecond, you will see all the population will be in 1 state. That means if you detect, because we always detect ground state, okay? If you detect, you will not see any population because the population is already been transferred to D state because you have applied pi pulse. So this is very important. Now it is this Rabi oscillation which depends on the strength of the quadruple transitions. The laser what you are using, it is related to the intensity of that one. Whether it will be fast or slower, mostly depend on the intensity. Again, the other thing, you cannot it is also not possible to have enough amount of power. But even if you have enough amount of power, you cannot apply all the power to drive these transitions. That has also bad effect. But what I want to point out here, so now we know what is pi pulse, how to transfer the population from H to D state, and we can bring it back because you can see it is coming back again. So if you apply 2 pi pulse, it is bringing back. So that is how we prepare our gate. Here you can see the X gate, which is Pauli gate, meaning if you apply, which is actually you can think it as a NOT gate, digital NOT gate. What digital NOT gate does? If your input is 0, if you apply digital NOT gate, the output will be 1, right? Similarly, if you apply quantum this X gate here, it will flip the bit, meaning if your initial state is 0, it will flip to 1 state. So it will be exactly similar to the digital NOT gate. So that is how you can prepare your gates. And here you can see like this r theta phi, what I have written it over here. This is the rotational matrix, and this here theta and phi, theta determines drive strength and time and the phase of the laser, and this is rotational matrix because in quantum computer only we can apply unitary gates in the terms of rotational gates, in the form of rotational gates, because you saw like a block sphere, right? Only rotational gates is possible. So whatever be the data you want to upload in quantum computer, it has to be converted in the form of angle rotational gates. Now, one more important thing I want to tell it over here. Okay, so this is the animation I wanted to show what is the meaning of X gate and Z gate on the block sphere. So another important thing I want to point it out, like superposition state. So you can prepare, so by optical pumping you can prepare zero state and one state, right? If you prepare zero state, you apply X gate and then you can prepare one state. But how about superposition state? How we are going to prepare it? So if you apply pi by 2 state, then you will prepare superposition state. So 50% population will be in the zero state and 50% population will be there in the one state. So that is how we create superposition state. Now, this Rabi oscillation, you see, till now I have not talked about any decoherence effect, but the contrast is like the contrast in the oscillation. What you are seeing, it is not always true. If you wait for a long time, the contrast will go down. That is because of there are many reasons, but because mostly it is because of the environment in terms of fluctuating magnetic field, or maybe the fluctuation of intensity of the laser which is addressing those two levels. So the first, I mean, what we have achieved, like fastest Rabi oscillation, which is 1.9 microsecond. So yeah, and the decoherence time is around 5 to 6 millisecond, which is sufficient for which was sufficient for our work. So if you want, I can take 5 minutes break here, then I can continue.
Yes, sir. It will be better to take a break now.
Yes, yes.
Yeah, and you can also see some queries in the chat box.
Uh,
So after the break, we can go through the queries, or towards the end of the lecture, also we can address those.